Welcome to today's Research Pays Off. I'm now going to hand it over to our speaker, Dr. Joe Sias of the University of New Hampshire. Joe, take it away.
Great. Thanks, Lauren. I'd like to present some of the work that we've been conducting under an NRRA study over the last few years and acknowledge the co-PIs on the project, Ishan Dawe at UNH, as well as Andrew Hands and Jerry Renke at MTE. So just a brief overview of what I'm going to go through today. We'll start with just an introduction of the program, of the project, orienting everyone to the main objectives and the scope. And then we'll go through some selected binder testing results, selected mixture testing results, and look at some of the pavement performance and have some discussions on what we're seeing so far with these materials, and then talk about what's happening in the next phase of the work. And then just as a note, since I'm just showing some select results, there is a final report that's available from the first phase of the project that has all the testing results and all for the binders and the mixtures available. So if folks want to dig into that a little bit more, you've got that resource available. So in terms of the study motivation and objectives, when this study started back in 2019, or even when it was, the conception for that project happened even earlier, we're really looking at recycling agents, being used to incorporate higher amounts of RAP. But at that point in time, there was very little long-term performance information, either from lab-based measurements or from the fields. For what we're expecting to see with these different materials over time and with aging. And there are concerns that a lot of folks had on the extent of the effectiveness of these materials over time. So that was the motivation that led to the project, where the objective really is to evaluate the effectiveness of 7 different RA projects or products that were put down in the fields. And really, it's not a focus on comparing the different products, but really looking at how those products compared to the control mixtures, looking at their properties in the lab as well as their performance in the field. And so, as I said, there's been 2 phases of the project. The initial phase 1 looked at performance in the field from, initial construction through 2024, and that's where a lot of the laboratory testing was conducted, and that's the results that I'm going to share today are focused on that phase 1 work. The phase 2 work is continued monitoring and testing that's going to be conducted over the next 3 years, and so that contract has just started, so I don't have any additional results to share at this point, but this will be continuing over the next few years. So you'll be seeing some of those updates at the Flex team meetings, and then also at the NRRA annual meeting and other venues. So these test sections were constructed in August of 2019. They're located in Emily, Minnesota. And you can see a typical cross-section for these test sections. Essentially, they were constructed on an existing pavement structure where there's 5 inches of an existing asphalt layer, where there was 2 inches of mill and fill done. And then the mixtures with the RAs were included just in the top 1.5-inch wearing course that was then put down on that mill and fill layer. So in terms of the pavement structure, we're really looking from the structural contribution of that top wearing course. But again, the focus is really on what's happening with these materials over time. And in terms of the materials in each of these test sections, so again, 7 sections, each with a different RA product. The mixes had 40% RAP. And so the dosage was determined by each of the RA producers with the intent of meeting a PG -34 target for extracted and recovered binder. So each producer had a sample of the RAP. and determine the appropriate dosage. So these 7 RA products are in test sections numerically ordered from 6001 to 6007. And then there are also 3 control mixtures. So there is a 30% wrap mixture. So that's the 6010. And then 2 40% wrap control sections, because these were constructed over 2 days. So there is a day 1 and a day 2. Now, one thing to note is during that initial phase 1 work, we found some issues with the day 2 control, the 40% wrap. So while we do have all the testing results are all included in the report, in terms of the comparison, we're just focusing on the day 1 40% control in the results. So one thing to also note with the different RA products, 6000, 6006, these were all added in line at the plant. The 6007 material was blended at a terminal. So while they have the same base binder, it's not exactly the same. It's base binder grade, it's not exactly the same base binder that was used in 6007 as for the other 6. Now the testing, okay, this basically through the kitchen sink at these mixtures. And so the mixture tests that were conducted, some mixture tests were conducted by various NRRA agencies, and then additional mixture tests were conducted at UNH. But we've got a range of testing from Hamburg wheel tracking tests, TSR testing, to rheological testing with the complex modulus, various fracture tests so the cracking tolerance index, direct tension cyclic fatigue, so fatigue testing that was done, disc shape compact test testing, low temperature, and then semicircular bend or IFIT testing was conducted on these mixtures as well. In terms of the binder tests, most of the binder testing was conducted by MTE, and this included 4mm DSR for the rheological characterization. And then that information was used to get the PG grade information from using the documented procedure for doing that from 4mm DSR testing. LAS testing was also conducted to look at the fatigue of the binders, and then SARA and FTIR was also conducted. Now, this range of testing was conducted on a lot of different aging conditions. So this is an overview. So we've got the 10 different test sections, and from those test sections during construction, plant produced loose mix was collected. That plant produced loose mix was reheated and compacted for testing, and then also conditioned in the laboratory, loose mix conditioning for 6 hours at 135. As well as 7 days at 95 degrees C. So 2 long-term aging protocols were used on the loose mix. And then for the field cores are being taken every year. So the data that I'll be showing today shows the first 4 years of field core results. Now, from both the loose mix and from the field cores, binder was extracted and recovered. So the material that was recovered from the loose mix, that was tested in the as extracted condition, so essentially short-term aging after it's been through the plant, and then additional 20, 40, and 60-hour PAV. We also extracted and recovered the material from the mix that had been laboratory, the 2 long-term aging conditions. Then from the field cores, the top ½ inch of material from the field cores was extracted and recovered for testing. And again, all 4 years were tested. I do have a note on the 3-year field cores. Unfortunately, we had some contamination issues with the material that it was extracted and recovered for those years. So I'm not showing that data. Again, it is shown in the report. But again, it's not exactly the same as what we're showing for the 1, 2, and 4 year. And then finally, during production, the binders were sampled in line, and those were tested in the original, after RTFO, and after 20 hours of PAV. So getting into some of the binder testing results. And again, I'm focusing here on just the extracted and recovered binder materials. So we're going to start with the rheological properties. So looking at the results from the 4mm DSR testing and looking at it in the form of the continuous PG information that comes out of that analysis. So what you're seeing here in these bar graphs is each group of bars represents each of the test sections. So you've got the 7 RA sections from 6001 to 6007. And then we've got our 2 controls. So we've got the 30% wrap, and the 40% wrap. And again, this is just the day 1 40%. In parentheses, you can see which day each of these materials were produced. Okay, so 6001 through 6003, those were produced on day 1. 6004 to 6007 were the day 2 production. Okay, but again, we're comparing everything back to the 30 and 40% controls. Now, within each set of bars, you have the results from the field cores presented first. So again, we've got the first year 1, year 2, and year 4 field core results. And then the next set of bars, okay, that have the yellow is the as extracted from the loose mix, and then the 6 hours at 135, and then the 7 days at 95. Okay, and the top are the PG high temperatures. Okay, the bottom graph is showing the PG low temperatures from the analysis. So what you can do is you can see in the field cores how these are aging in place over time. Okay, and for most of these RA sections, obviously we're seeing an increase in the PG high temperature. For most of them, 6006, there's not a whole lot of change that we're seeing on the high temperature side of that one. And you can see they're, for the most part, okay, showing what we'd expect to see in terms of changes over time in, in the laboratory, or in the field, based on the laboratory measurements. Okay, for the mix that was aged in the lab, okay, we can see the 6 hours is less severe of an aging condition than the 7 days at 95 degrees C. And then you're seeing similar things when you were looking at the low temperature grade. Okay, again, we're losing some of the low end in the fields pretty consistently for these different products over time. Okay, and again, the 7 days is much more severe than the 6 hours at 135. And if you look at these kind of overall, okay, all the RA mixes, okay, are showing cooler, low temperature, okay, than the controls, even after 4 years of aging. Okay, so they're still doing what they we're expecting them to do on the low temperature side, okay, over those 4 years. Okay, and then the 7 days at 95, okay, all of those RA binders are getting very close to the 40% control mix, okay, at that longer aging, with one exception, the 6006. Okay, that one's showing a little bit different behavior, okay, higher high temperature grade and a warmer low temperature grade. more substantially different than most of the other ones that we're seeing. Now we can also look at the delta TC. Okay, so staying with the rheological properties, delta TC values, again, we're seeing the same grouping of the data in terms of the field cores and then the material that is extracted and recovered from the loose mix that's been aged. You can see that the as extracted, so the yellow bars for each of these start with positive delta TC values. Even the wrap ones are starting mostly with positive delta TC values. And then we're seeing over time with the aging in the fields, we're seeing those delta TC become more negative as we'd expect. And then with the laboratory aging, the 6 hours, and then we're really seeing larger changes with that 7 days at 95-degree aging. All of these materials in terms of the field cores, they are still below any kind of warning limit. Okay, even after 4 years, so they're not at the level where we'd be concerned based on that crack warning limit. Same with the 6 hours at 135. But then once we get to the 7 days at 95 degrees C, okay, these become, they're exceeding the crack warning. Some of them are exceeding the cracking limit or approaching that cracking limit. And almost all of them are worse than the controls at this point. Whereas, for the less severe, the 6 hours at 135, and then even through the 4 years, they're usually equivalent to what we're seeing with the control mixes. But the long-term aging, that longer-term aging, we're starting to see some differentiation from the controls and between some of the different mixes. Okay, now we can also look at, plotting this a different way. So we've got a series of figures that I'll show here that shows the change in the different parameters as compared to the 30% control and as compared to the 40% controls. Okay, so if we look at the figure in the upper left, okay, so this is for 7 different series of data. So each of the RA mixes, and just looking at the relative percentage, okay, with as compared to where we're seeing the control mix. So you can see most of these mixes, okay, are with the field aging getting closer to both the 30% control and the 40% control over time. Okay, with the one exception of the 6006 where it's showing a lot bigger difference. Okay, so if it's a more positive difference, okay, it's a lot worse than what we're seeing with the controls. So that's with the field aging, the 2 plots on the left, the 2 plots in the middle shows what's happening with the PAV aging. So again, as a reminder, this is the as extracted material as it was produced and then recovered and aged for 20, 40, and 60 hours. And you can see again the as extracted materials, okay, and then 20 hours. Okay, there's quite a wide spread in terms of the differences with the 30% control, but then once we get to the 40 and 60 hours, you can see those coming together, really grouping, and basically we're seeing kind of that saturation happening with the aging, less differentiation, and coming closer to what we're seeing in terms of the delta CC for the control mixes for both the 30% and the 40%. And then finally, the last set, this is looking at the loose mix aging. Again, we've got a wider range of values in terms of how they're what their properties are compared to the controls at the as extracted. 6 hours, again, depending on whether you're looking at the 30% or the 40%, things are coming a little bit closer together. Okay, and then even more so once we start looking at that, the most severe long-term aging, loose mix aging condition. Okay, moving on to the FTIR. So FTIR, what I'm focusing on here is just the carbonyl ratio. So again, same set of bars where we've got the change with the field cores, okay, and then the change with the different laboratory aging protocols. Okay, now with both of these, we're seeing that increase in the carbonyl ratio for the most part with all these different RA products. Okay, and then we're also seeing, generally higher carbonyl ratios than the controls for all the different aging conditions. And this is expected just because of the chemistry of these different materials that we would see the different carbonyl ratios. So really, focusing on how these are changing over time with the field cores and then also with the laboratory aging. So similar types of plots that we looked at previously, showing the same things for the actual carbonyl ratio values. With the field aging, okay, again, in terms of the spread, okay, in terms of how these change from the control values, not a lot of differentiation in terms of it changing a whole lot from the controls with the field aging. So we're still not seeing a lot of difference there. But when we look at those PAV aging, again, as we get from the 20 to 40 to 60 hour, we're seeing those groupings come a lot closer together for, when we compare them to both the 30 and the 40% control. And again, this is something that we'd expect to see, where as we age them longer, things are getting closer in terms of, those properties. Same thing we're seeing with the loose mix aging. As extracted 6 hours, and then the most severe, the 7 hours. Again, the groupings are much tighter together. All right, so moving on to some of the mixture testing results. Okay, we'll start again with the rheological properties. So we're starting with some of the results from the complex modulus testing. And what I'm showing here is the Glover-Rowe mix parameter. So it combines stiffness, dynamic modulus, and phase angle value similar to the Glover-Rowe for binder. And then one thing to note, because we're looking at field cores, when we do the testing on the field cores, we have to test them at whatever the field core air void content is. When we tested the laboratory mixes, we have control in the fabrication process, and those were all fabricated to the 7% air void content. So to do these comparisons, what we've done is adjusted the field core results to an equivalent 7% air void content. And the process for doing that, again, is detailed in the report, but it's a way to try to, essentially get everything at least a little bit more on an even playing field, since we don't have the ability to control the air void content of the field cores. Now, with the mixed results, we do have the 3-year field core results in here. So you can see that additional orange bar for those results. Everything else is set up the same in terms of what we've talked about before, with the field cores presented first, and then the reheated plant mix and the 2 long-term laboratory loose mix aging protocols. So you can see, similar to what we were seeing for some of the binder results. Okay, the field cores, depending on the mix, you are starting to see after a couple of years some changes, increases in that Glover-Rowe mix parameter, and indicating that we do have higher stiffness or lower phase angle, combination of the two happening over time. But in terms of looking at how the controls are doing over that same time, most of these RA section materials from the field core perspective, are equal to or better, meaning lower Glover-Rowe mixture parameter than the controls through 4 years in the field. When we look at the reheated plant mix, the initial state, and then the 2 longer term aging conditions, again, we're seeing a lot of difference when we go to that more severe 7 days at 95 degrees C. You can see that quite clearly with those brown bars, but still, even after that level of aging, most of these RA materials are still showing a better property than the controls, even at that long-term aging condition. Okay, so we've done the same thing in terms of looking at the change from the 30% and 40% control mixes. So again, positive value means, it's a lower Glover row mix property, which we'd expect to be better cracking properties and performance in the field. So if we look on the left-hand side at the field aging, you can see, again, pretty steady in terms of not seeing a whole lot of change through the 4 years of field aging for most of these mixes. Again, a couple of exceptions with the 6002 and 6007 when we look at how they're doing compared to the 30% control, and then not as much of a change, but still seeing that change with the 40% control as well. For the loose mix aging, okay, kind of similar to what we saw for the binder testing, where the 6 hours at 135, again, we still see quite a bit of spread in terms of the rheological parameter for the different RA mixes. And then 7 days, we're seeing things starting to come a little bit closer together. But again, the exact, difference from those control mixes, it really depends. It varies from RA product to RA product in terms of the magnitude of the difference. And some are showing better, some are showing worse in terms of, relative properties. Okay, so next let's look at a fracture test. So intermediate temperature fracture using the iFit test to show this parameter. One thing with this test, you'll see one additional aging condition. So this was an additional aging condition that was conducted by the agency that did this testing. This was a long-term aging of 3 days at 95 degrees conducted on a compacted sample. So a little bit different, but I wanted to show this data just for comparison. With the iFit tests, again, a note that for these field core specimens, these are the results with the in situ air voids. Okay, and the lab specimens are 7% air voids. So there is a difference between the field core and the lab specimens. So there wasn't an adjustment done on these parameters. But you can still look at kind of overall what we're seeing for that intermediate temperature fracture. The reheated plant mix, those yellow bars, a lot of these mixes have pretty good values. We see the benefit of the addition of the RAs, especially at, just with this reheated material. Okay, so initially you're seeing the benefit for this intermediate fracture, and even after 6 hours at 135, most of these mixes, you're still seeing some benefit over the two controls. But when we get to the longer term aging, okay, basically everything's coming down closer to what we're seeing for the control values. And also in the fields, once we get to 3-year field core results, okay, very few of these met the cracking thresholds. Okay, and all of the mixes, including the control, fail the threshold value at that longer term aging condition. Okay, so even though we have kind of better flexibility index values, okay, for the 3-year field cores, okay, they're still everything's still below the threshold. And again, 6 hours, we're still seeing some of that benefit, like I mentioned previously. Okay, so then when we plot these in terms of the relative changes, okay, for the flexibility index, in terms of the field aging, okay, you can see, and we're seeing an increase, okay, in terms of both control values, but again, there's a little asterisk there that even though you're seeing better values, they're still failing the threshold. Okay, and then looking at the different loose mix aging, okay, again, we're not seeing a whole lot of change in terms of their relative difference with the controls. Okay, for some of the mixes, some of them we're seeing them come closer to the controls. Okay, but again, you got to remember what the absolute magnitude of some of these values at the higher aging conditions where everything's failing the threshold value once we get to that point. And then moving on to the low temperature fracture test. So this is the DCT test results. Okay, this is a little bit of a different parameter than folks might be used to seeing with the DCT. So this isn't the fracture energy, but this is an index that also includes some of the post-peak information. So it does more than just looking at the fracture energy. It looks at what the shape of the curve is on the post-peak side. And here for the DCT, we don't have any results for the field cores. We just have the results from the laboratory mix. So we've got the reheated and then the two longer term aging conditions. Test temperatures on these were done at the location PGLT for the location in Emily plus 10 degrees C. So the test temperature was negative 24.8. And all these are done with lab specimens, again, with 7% air voids. Okay, so you can see how these are changing. Not as much of a change for the low temperature fracture with the aging as we saw with some of the other parameters, perhaps. But most of the mixes we're seeing in terms of their relative values, okay, we're seeing benefit with the reheated and the 6 hours, but then once we get to that longer term aging condition, the 7 days at 95, okay, they're getting to the point where they're effectively matching what we're seeing in terms of the value for the control mixes. There's 6005 still showing a little bit of benefit, 6001 a little bit as well, and a couple that are a little bit lower, but we're essentially getting to what we're seeing from the controls at that longer aging level. Okay, and you can see that again with this plot here, okay, showing that we do see the differences of the reheated 6 hours at 135. Again, depending on the mix, some are a little bit better, some are a little bit worse. Okay, but then once we get to the 95, you're seeing from most of those RA mixes are coming very close to both the 30% and 40% control values, with the exception of that 6005 and 6007. One's showing better, one's showing a little bit worse. Now the actual performance of the test sections. Okay, so we'll show the cracking field performance. And so this is a function of the service time. So multiple surveys have been done. And again, this is just showing through just over 4 years of in-service. So the last data point that we've got on these figures is, I think it's November of 2023. So additional information has been collected. It just hasn't been collated and added in yet. So the plot on the left is showing the length of cracking, okay, as a function of time. Things that I want to point out here, the one that's showing the least amount of cracking, that dotted black line with the square, that's the 30% wrap control. Okay? And then the one that's showing the most cracking after this time in service, that's the 40% wrap control from day one. All the RA sections are falling between these two controls in terms of the crack length. You can see some are starting to take off a little bit. We'll see what that's doing with later field performance. But then we've also taken these okay, and converted into the TC total index, okay, which is basically looking at, it's a way of looking at the area under these curves. So it not only accounts for the actual magnitude of cracking, but when these different sections are cracking. And again, here looking at this index parameter, the 30% control and the 40% control, okay, looking at the right, all of these RA sections are falling in between these two. The 6004 is the one that's closest to 30% in terms of the field performance. But again, everything's in between these two control values. And really what we're seeing is, for the cracking, 4 years of field performance, really not enough to differentiate any of these mixes. And then in terms of the rutting and the ride quality, rutting is shown on the left, again, over time, and IRI representing ride quality on the right. We're seeing, a little bit of rutting, but really, again, not substantial amount of rutting in any of these sections. The one that's the highest, this is the day 2, 40% control. The two other controls of 30 and 40% are, kind of the lowest rutting. So, with the dosing that was done with these RA materials, didn't produce any concerns in terms of the rutting. And then again, in terms of the ride quality, we're starting to see a little bit of an increase in the IRI, again, probably related to the increase in cracking that we're seeing in the later years. But again, still nothing substantial in terms of magnitude and really not a lot of difference that we're seeing in terms of the different sections. Now, the other thing that we did was, because we've done both the complex modulus and the direct tension cyclic fatigue, we're able to run these in FlexPave and look at the performance prediction from a fatigue standpoint with the actual pavement cross sections. So what you're seeing here is the predicted total damage from this analysis after a 20-year analysis period. And this is done with 2 different sets of results from the testing. So based on the reheated plant mix, that's what you're seeing with the yellow bars. And then based on the values that were collected from the testing that was conducted on the 4-year field cores, that is the black hashed bars. Okay, so a range of different aging conditions. And really what we're seeing is not a whole lot of difference between the different mixes. And again, remember that the only difference between the sections is that top 1.5 inches. So when we're looking at fatigue, there's not a whole lot of contribution from the different materials in terms of the overall structural performance of these sections. But regardless, everything is still falling between the 30% and the 40% control materials. Okay. So just to summarize some of the key findings from the binder analysis, what we saw was the RA mixes are generally showing similar or better low temperature PG and delta TC than the 40% control mix through 4 years of field aging. Most of those RA mixes have a worse delta TC when we're looking at that long-term loose mix aging condition. Okay. And, again, as we expected, because of the chemistry, we're seeing higher carbonyl ratios than the controls, and that goes through all of the aging conditions. From the mixture side, okay, we're seeing improved properties for most of those RA mixes for 4-year field core and for the 7 days at 95 degrees C. In terms of the threshold values, if we look at the flexibility index, and everything's falling below that threshold at that long-term aging condition. But when we look at relative property values, the RA mixes are still showing better values than the controls at the different aging conditions. And then RA mixes initially were showing better low temperature fracture properties, okay, but then really coming to the same level in terms of the property values, okay, or even worse than some of the controls after that more extensive aging condition, laboratory aging condition. Field performance, okay, again, we're still seeing mostly better cracking performance than the 40% control over 4 years. Okay, we're not seeing any rutting or ride quality issues. Okay, and really what we're seeing is that 4 years is not enough to evaluate that longer term performance in the field. From the perspective of the aging protocols, that 7 days at 95 degrees C, okay, so far that's definitely more severe than what we observed with the 4-year field core results. The 6 hours at 135, when you're looking at the different properties, okay, these are comparable some to the 3 to 4 year field core. So for this location, that 6 hours represents somewhere between 3 and 4 years of field aging in terms of what we've observed in that top half inch. So what we're looking at doing, phase 2, again, continuing monitoring these sections and sampling field cores. So we actually have the cores that were sampled in 2024 sitting in our lab ready to go. And some of the binder testing has already been conducted. So we're maintaining the testing that we're conducting on from phase 1 for the additional field cores. So the mixture testing as well as the testing of the extracted and recovered binders. We are doing additional IFIT testing on the field cores for the future years, and continuing to evaluate the different testing methods and the parameters over time in terms of what we're seeing between the laboratory and the field in terms of what's the appropriate way to look at these materials in the lab to correlate best to expected field performance. Okay, so that will be continuing for an additional 3 years. And with that, thanks for your attention. And happy to take any questions or comments at this point in time.
Thank you, Joe. I am not seeing any comments from during the presentation, but if anyone has any questions or comments, feel free to unmute yourself and ask. Well, you must have done just an excellent job explaining everything makes sense to everyone.
Well, if folks have questions later, just feel free to reach out to myself and or Ishan, and we're happy to answer any questions that come up. And again, just reference to the full report that has all of the details in that, and just keep an eye out for additional updates as we get some additional data on these mixtures over time.
Sounds great. Well, I see some folks have jumped off. They probably have other meetings they got to get to soon. So, well, thank you again. And I will just adjourn us a little early today. Thanks everyone for being with us, and we hope to see you next month.
Thank you.